So this is chapter 2 in Biology 160. We're looking at the chemical context of life. So in this chapter, what we're starting to look at are some of the basic chemicals and review some basic chemistry that's involved in biology. Matter is anything that takes up space and has mass, and chemistry is just the study of matter. Anything that is alive is definitely going to be made up of matter, so that makes biology and chemistry inherently tied together. The elements are the substances that cannot be broken down any further through chemical reactions. So if you were to break them down into their subatomic particles, they're no longer going to maintain the properties of that element. When you look at a periodic table, all of those different symbols in the different boxes are the different elements that we have. A compound is just two or more elements combined in a fixed ratio. So that would be something like H2O with water. You've got hydrogen and oxygen, and they're in a fixed ratio of 2 to 1. A molecule is going to be two or more atoms of the same element. So that would be something like O2 or N2 gas, where it's just one element and there's more than one of them involved. For the elements involved in biology, there's a relatively limited number of them. They are the essential elements. It's about 25 of them total. Carbon, oxygen, hydrogen, and nitrogen make up 96% of them. So they are the vast majority. Then you've got phosphorus, sulfur, calcium, potassium, and a few others that make up the majority of that other 4%. We have some trace elements. These are required in minute quantities. They're actually toxic if you have them in more than minute quantities. So these would include iron, iodine, sodium, magnesium, chlorine, zinc, copper, cobalt, chromium, boron, fluorine, manganese, molybdenum, selenium, silicon, tin, and vanadium. So if we look at the structure of the different elements, we start with the atom, which is the smallest unit of matter that retains the properties of the element. They're going to be made up of subatomic particles. The mass of the proton and the neutron are each 1.7 times 10 to the negative 24th grams. The electrons are about 1/200th of that size. The other subatomic particle we have is going to be the electron. So you've got protons, neutrons, and electrons that make those up. Protons are going to be found in the nucleus. They have a positive charge. Electrons are found outside the nucleus, and they have a negative charge. Your neutrons are also in the nucleus, and they're going to have a neutral charge. So since these are so small, 1.7 times 10 to the negative 24th grams is a very small number to work with. We use the AMU or Daltons as the units instead of grams. So your atomic number, this is going to tell you the number of protons that are in that element. That number is unique to that element. Your mass number is going to be the mass. It's going to be the sum of the protons and the neutrons. You can actually deduce the number of protons because in a neutral atom there's going to be a number, you're going to have an equal number of protons and electrons. So for example here, if we look, you've got this 4/2 for helium. Helium has 2 protons and 2 electrons. So when you take 4 minus 2, that's going to tell you that you've got 4 neutrons. With sodium, we've got 23/11. Sodium has 11 protons and 11 electrons. So 23 minus 11 would be 12 neutrons. Hydrogen is a little unique in that it has no neutrons. It just has 1 proton and 1 electron. There's different models of looking at the atoms. These are 2 simple basic models. One of them is this cloud model that looks at where you are most likely to find the electrons hanging out. This one is your planetary or orbital or Bohr model. This has different shells around the outside of the nucleus where your electrons are most likely to be hanging out. So the atomic mass is the total mass of the atom. It's the mass of the protons and the neutrons. Each of those is close to 1 Dalton, so the mass number is going to be an approximation of the total mass. So with sodium, the mass is 23 AMUs or 22.9898 AMUs. So again, the AMU is atomic mass units. Your isotopes are the different atomic forms. So these can have more neutrons than the other atoms of the same element and have a greater mass. So they'll still be the same element because they have the same number of protons. So in nature, things are going to occur as a mix of isotopes. For example, carbon-12 is 99% of the carbon in nature. It's not necessarily an equal mix. So carbon-12 is going to have 6 neutrons, carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons. So although they're going to have different masses, they're going to behave identical in chemical reactions. So the radioactive isotopes are one in which the nucleus decays spontaneously, and it gives off particles and energy when it changes the number of protons as it transforms the atom to a different element. So this energy given off is what makes them radioactive. So while radioactive can be harmful, it can also have some useful properties. So it can be used in radioactive dating. We're not likely to run into that much in health occupations. Generally, if something's old enough to use radioactive dating, you're not going to be doing anything with it in healthcare. It's far beyond it. You can use them as traces to follow atoms through metabolism. Here's where it's used a lot in healthcare. It will allow you to see if you wanted to say, okay, I'm going to take in some iodine here, and I want to make sure that this iodine is all going to the thyroid. You can use radioactive iodine, and then you can actually detect where the radioactive material is in the body to make sure you can see where it is going. If you're not sure where it's going, this is a way of being able to say, all right, who is metabolizing this in the body? So it's useful in research in medicine. However, it is hazardous because it causes some cellular damage. So anything like that, you always want to look at it and say, does the information I am going to gain from doing this study offset the risks to the patient? When you look at energy levels in electrons, your energy is the capacity to do work or cause change. So we've got two main forms. Your potential energy is the energy due to the location or structure. Your kinetic energy is your energy of motion. When we look at the electron shells, these shells have a characteristic average distance and energy level. So the electron energy correlates with the average distance from the nucleus. So the distribution of the electrons will actually help determine the chemical behavior. And what we're most concerned about are the distributions of the atoms in the shells, particularly the outermost shell. These are your valence electrons, and their chemical behavior of the atom will depend on the number of valence electrons. So if you have a full valence, that outermost shell is full, and the atom's going to be inert. So all the others are chemically reactive if they don't have a full valence. So an incomplete valence will lead an atom to be more reactive. So on this periodic table here, this is actually missing a section out of the middle. What we see here, all of these have an outer valence that's full. So your first shell would have 2 electrons to be full. Your second and third shells both have 8 electrons. This model doesn't work real good beyond looking at the third shell. So just look at it for the size molecules that it's meant for. It works well to keep a simple explanation here in biology. So here on the far right, all of these have a full valence. They're called the noble gases or inert gases because they have everything they want. They're not going to be very reactive. Over here on the far left, you have the exact opposite. So the outermost shell only has 1 electron in there. It's not even close to being full. So in nature, these won't even exist in this state. They will be very aggressive at getting rid of that electron so that they can have a full valence below that and be more stable. Over here, these have 2 in their outermost shell. They're going to be pretty aggressive at getting rid of those electrons as well. Then when you come over here on this side, these are just 1 short of having a full valence. So fluorine and chlorine here both have 7 in their outermost shell. They're going to be very aggressive at seeking out an electron. So we call that being electronegative, and fluorine is the most electronegative molecule on the periodic table. So there's a couple different models we can look at this with. The two-dimensional model uses these concentric rings that represent the orbital shells. In reality, you'll never know the exact location of an electron. Instead, what it's describing is where it's going to spend most of its time, about 90% of its time. The electrons move very quickly, so if you identify its location at one point, it's not going to be there just a fraction of a second later. So what we do is look at the probability of where you're going to find it most of the time. So this is an example here of looking at your two-dimensional model. The three-dimensional model is going to use these dumbbell-shaped orbitals, and they're going to be in the x, y, and z axis with no more than 2 electrons in each orbital. Here you're going to have your first shell is your 2s, and then next is the 2s, 2p, where we look at the x, y, and z orbitals in the second shells. So we're not going to go into the details of that model in this class. We will save that for chemistry, but that works better when you start to look at the bigger molecules. So your reactivity arises from an unpaired electron in one or more of the valence orbitals, and they interact in a way to try and complete their valence shell. So this is your two-dimensional model here. Just below you can see here is your three-dimensional model looking at these different orbitals in the x, y, and z axis. So when we look at chemical bonding, what we're looking at is the bonds that are going to form between molecules, and this will determine their function. So a chemical bond is just the interaction of the electrons between atoms, and this is what holds them together. The strongest are the ionic and covalent bonds. Covalent bonds are going to involve sharing a pair of electrons, and we're sharing the valence electrons between two atoms. So hydrogen, each of these has one valence electron. It would like to have two in that shell. So when their shells get close enough to overlap, they will actually both have access to two electrons. Two electrons will pass through their little cloud, and so then the molecule will be happy and they will be held together. So this would be your H2 molecule. This here is showing your two hydrogens with it drawn out on the shell, where their shells overlap enough and the two electrons are going to be there holding them together. So there are different ways that we can make models of molecules. The Lewis dot structures uses the elemental symbol with dots around representing the outermost electrons, and then you use a single line to represent the single bond or pair of shared electrons. So here with the H2, Lewis dot structure has the two dots which become this line. This space-filling model just tries to give you a little bit closer to a three-dimensional view of what they would look like. With oxygen here, you can see you're going to have 6 electrons and 6 electrons so that they overlap a little bit. You have a double bond holding the two oxygens together. With water, you can see that the hydrogen is going to share with the oxygen, and it's going to do that with 2 different hydrogens actually for each oxygen. And then here down at the very bottom you can see methane. Methane is a nice example here of covalent bonding. So you've got this carbon here that has 4 electrons in its outermost shell. It's going to share with 4 different hydrogens, which will each bring an electron, so that you can have a total of 8 in that outermost shell when they are shared. And so carbon will make these 4 single bonds here that are covalent bonds. So when we talk about the valence of an atom, it's its bonding capacity, the number of unpaired electrons to complete the outermost shell. The electronegativity is the attraction for the electrons of the covalent bond. So the more electronegative you are, the more strongly you're going to pull electrons towards yourself. So again, our most electronegative atom is going to be fluorine. When sharing, you can have a polar covalent or a non-polar covalent bond. With the non-polar covalent bond, the electrons are going to be shared equally. So they all have equal electronegativity. Here with the methane, they all have equal pull going around this molecule. None of the hydrogens wants it more than the other. When you have a polar covalent bond, one atom is going to be significantly more electronegative, and the electrons don't end up being shared equally. So if we look at water here, what's going to happen is you've got the 2 hydrogens that are sharing electrons, but the oxygen also has a couple of these other electrons of its own. These electrons are going to be shared, so they're going to be more likely to hang out in this region between the oxygen and the hydrogen. So that's going to give this region over here of the hydrogen a partial positive charge when the electrons are not there. Over here with the oxygen, it's got these extra electrons that it had on its own that are not part of that shared relationship. they're going to be hanging out over on this side, which will give it a partial negative charge on this side. So when we look at this, what you end up with in the water molecule is two partial positive charges where the hydrogens are, and a partial negative charge on the side where the oxygen is. So this will allow it to form hydrogen bonds, which is going to be the attraction of the partial charges that are created by polar covalent bonds. So you could actually have this portion of a water molecule attract to this portion of another water molecule. And we will look at that more in the chapter on water, but it explains a lot of the properties of water. In your ionic bond, you're going to have the electronegativity difference strong enough that it actually pulls an electron away from its partner. So here, when you look at sodium, this single electron here is going to get pulled away. It will become positively charged because it didn't lose a proton, it just lost an electron. So we call it an ion when you have a charged atom or molecule. Because this one becomes positive, it's going to become the cation. The chlorine will take that electron and add it to its outermost shell to fill it up. So it will have more electrons than protons and become negatively charged, or the anion. So in an ionic bond, you have this attraction of the positive and negative charges here that are going to hold these two together and create the ionic compound. So ionic compounds, or salts, are formed by that positive and negative attraction. So table salt is the example with sodium chloride, but there are other salts out there in chemistry that are not table salt. So table salt has what we perceive as a salty flavor, but the others do not. So the strength of the ionic bond is going to depend on its environment. When they're dry, they're very strong. But when they're dissolved in water, they become much weaker and will actually come apart. So when we look at these weak chemical bonds, the hydrogen bonds are important for living cells. It's going to create the surface tension of water. That's what's going to allow bugs to walk on the water and not break through the surface. If you fill up a glass of water and you can see the bubble form on top of the glass, that again is also the surface tension of water. So this is showing here your partial positive and partial negatives creating the hydrogen bond. The van der Waals interactions, these are another type of weak bond. Here the electrons are not symmetrically distributed. So even if it's a nonpolar covalent bond, at any moment they might accumulate a partial charge. So the ever-changing region of possible positive and negative charges allows the atoms and molecules to stick together, but it only works when they're very close. So it's kind of like having all of those electrons moving around, but some of them will kind of hold up traffic, and you can have them clustered in one area temporarily to create that partial positive or negative charge there. So these are going to explain why lizards can walk on walls. They have little hairs that are able to make those bonds. So this works for the little guys. You're not going to find big reptiles walking on the walls. You don't have to worry about finding a crocodile walking on your wall. They're too heavy. Gravity is going to pull on them stronger than what these bonds will hold them to the wall. So when we look at the molecular shape, this will tie in with its function. If you've got two atoms, they're always going to be linear. If you've got 2 points, the only distance between them is always a line. When you have more than two atoms, the shapes become more complex. So if we look at water here, you're going to have a bond between them of 104.5 degrees. You've got this unpaired, unbonded electron pair here that's actually going to help to repel things against. Everybody wants to be spread out as far apart as possible, including these unbonded electron pairs. So methane is going to give you that similar shape here. So the molecular shapes are crucial in biology because it will show how they interact with specificity with other molecules. If we look at the opiates, for example, they have a similar shape to endorphins, so they bind similar receptors. So here you can see on the natural endorphin, this is going to be the part that will bind to the receptor. Morphine has a part that's going to look just similar enough that it will fit in the receptor. So in the brain cell where you've got these endorphin receptors here, you can have the natural endorphin bond to it, but morphine will also bond to it. This is a very common principle looked at in pharmaceuticals. If you've got a chemical that can bond with something, the pharmaceutical agent or industry can always try and create something that will fit in that space, create a bond, and trigger a similar response. So when we look at chemical reactions, this is when you're going to make and break chemical bonds. This will lead to changing the composition of the matter. The reactants are your starting materials. When you look at the equation, they're going to be these things on the left. Your products are the end materials. They're over here to the right of the arrow. In this example of photosynthesis, you've got 6 carbon dioxides that are going to react with 6 waters to make 1 glucose and 6 oxygens. This big number here in front is going to be the coefficient. It indicates the number of molecules involved. So for every 6 carbon dioxides, you're going to need 6 oxygens to make 1 glucose, and it will give you 6 oxygens. And I'm sorry, that was 6 waters. If you were to change this and you had 6 carbon dioxides but only 4 waters, you're not going to be able to make your glucose and oxygen here. You're not going to have all of the ingredients. So you can think of it as kind of like the proportions of things that you have if you're going to make some cookies. If you want to make a triple batch of the cookies, you have to triple all of the ingredients, not just some of them. Otherwise, you're not going to get the same thing. So chemical equilibrium is the point at which the reactions offset each other. So a lot of reactions are actually reversible. They can go both ways. The amount of your reactants that will turn into products will vary as well. So we tend to look and assume they would all turn into products, but if you've reached equilibrium, you're going to stop having the reaction progress with a net gain in that direction. So the reactions are still going in both directions, they're just not going in one direction faster than the other anymore, so that you won't have a relative buildup of one of the other, either the products or the reactants.